So Greg's Steam account contains 36 games made up of RPGs and puzzle games. The probability of choosing an RPG is 4 times as likely as choosing a puzzle game. How many types of each game does Greg have? All right, so if we take RPGs and we take puzzles, well, the least number of puzzle games we can have is 1. And if we have 1 puzzle game, that means that Greg has 4 RPG games. So what that means is that the probability of choosing an RPG is 4 out of a total of 5, because 4 plus 1 is 5. Now we can use that then, and I said in class that this should have actually been 35. So if we go over 35, then this is x, and now we just cross multiply. 4 times 35 is 140. That equals 5x. Divide both sides by 5, and we find that Greg has 28 RPGs. But that's not the only thing that we're asked to do. So we want to know how many, it should be how many games of each type does he have. That's what I get for writing these things myself. So we take 35 and we subtract 28 and we get 7 puzzle games. Number 2, you roll doubles 10 times in a row. As you continue to roll the dice, the result of doubles increases. What will happen to the theoretical probability? Well, what will happen? It stays the same. Theoretical probability does not change just because experimental probability does. So theoretical probability remains constant while experimental probability changes. Use a tree diagram to find the sample space and total number of possible outcomes. So we've got apple, banana, and pear. So that's A, B, and P. We then have 3 drinks. We have water, ice, and milk. We have water, iced tea, and milk. And we have water, iced tea, and milk. That makes 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. So use the fundamental counting principle to find the total number of outcomes. So we have 1, 2, 3, 4 times 1, 2, 3, 4, 5 times 1, 2. Well, 4 times 5 times 2 is 40. So there's 40 outcomes. It says, what's the probability of randomly choosing banana and milk in exercise 3? So going up here, banana and milk appears only once. So we have 1 out of 9. On a sheet of stickers, the probability that you choose green star is 1/5, which makes it unlikely. On a sheet of stickers, there are no purple stickers. What's the likelihood of choosing something purple? Well, it's impossible. On a sheet of 30 stickers, 6 of them are green stars. What's the probability of choosing a green star? Well, that's 6 out of 30, which is 1 out of 5, which is 20%. But choosing a green star in your second choice, well, what happens then is that the first one, we chose the 30 stickers, so now we're down to 29. Secondly, we had 1 green star already, and so now we're down to 5 green stars. So that's 5 out of 29. Leave it there. You purchase a large board game. The theoretical probability of choosing a legendary treasure from the treasure deck is 15%. So legendary is 15%. The treasure deck contains 51 non-legendary treasure cards. How many treasure cards are in the deck? So we're given non-legendary, so we need to actually find the non-legendary. We go 100, probability of selecting a non-legendary, Probability is, 100 minus 15, which is 85%. So that's the probability of choosing a non-legendary. which means there are 51 legendary cards is 85% of the total deck. And so if we use our proportion, we'd have 51 over W equals 85 over 100. So that's 5100 equals 85W. Dividing both by 85, we get that W is 60. So there's 60 treasure cards. If you flip a coin and roll the 20-sided figure, well, our sample space for flipping a coin and rolling a 20-sided figure is going to be 2 for the flipping of the coin times 20 for the rolling of the die. And the probability, the sample space for the probability is 1 heads, and then rolling less than 3. Well, there's only 2 numbers less than 3, so that's 2 out of 20. So we go 2 over 40, which is 1/20th, which is 5%. A medicine is effective for 80% of the patients. The table shows 30 randomly generated numbers from 0 to 999. Use the table to estimate the probability of the event. The medicine is effective on fewer than 2 of the next 3 patients. So fewer than 2, probability of fewer than 2, that means less than 2, which means what we're looking for is we're looking for 80% of the patients. We're looking for 1 through 8 to only appear once or not at all. So if we look through here, we're just going to look through and we're going to highlight the ones that have 1 success or less. So 463 has 3 successes. 013 has 2 successes. This one's 3 successes, 2 successes, 2 successes. 3 successes, 2 successes, 3 successes, 3 successes, 3 successes, 3 successes, 3 successes, 2 successes, 3 successes, 3 successes, 2 successes here, 2 successes, 3 successes. Ooh, this has 1 success. This has 1 success. 3 successes, 3 successes, 3 successes, 3 successes, 2 successes, 1 success. 3 successes, 2 successes, 2 successes, 2 successes, 2 successes. So what we find here is that we have 3 3 events that we were looking for out of the whole 30, which is 1/10, which is 10%. We want to know what we can simulate with a coin flip. And Archer hit, so making sure you understand this, the probability of a coin flip is 50% heads and 50% tails. So we're looking for things that are 50%. And Archer hits a target 50% of the time. We can represent that with a coin flip. There are 6 numbers on a die. You roll a number less than 5. Well, that's not going to work because there's actually 4 numbers less than 5. Open a card pack and getting a legendary has a 5% chance. That's not going to work. You roll an even number on a number cube. That does work. And the sex of a newborn kitten is equally likely as not to be female. That works. Okay. Last of these. 2 beakers are used in a lab test. What's the experimental probability that there are reactions in both beakers during the lab test? So we're looking, in this case, for 1 through 8 and 1 through 5. So the way I would go about doing this is I would look for the ones that have a 1 through 5 at the end of the number and then go back and evaluate those based off of 1 through 8 being the first number. So if we look through here, I'm just going to highlight the ones that end in 1 through 5. So I'm going to ignore 98 because it doesn't end in a 1 through 5. And I'm going to ignore 97 because it doesn't end in 1 through 5. I'm going to keep this one for a moment, keep this one, 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 keep this, 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 keep this one, keep this one, keep this one, oh, no, I don't want that one, eek. Let me erase that. Keep this one, keep this one, keep this one. So those are the ones that I've kept based off of the Beaker 2 being successful. Now I'm going to go back through and I'm going to look for the ones that actually are successful from there based off of the numbers 1 through 8. So if the beginning number is a number 1 through 8, I keep it. So that one's gone. Oops, I want to do this in a different color here. That one's gone. That one's gone. Keep those. Get rid of this one. Get rid of this one. Keep all these. Keep all these. This one's gone. And so these are the ones that I'm left with. So what I'm left with is I'm left with 2 here, 2 here, 2 here, 1 here, 3 here, 4 in this column, 2 in this column, 1 in that column, 2 in that column. So doing some quick addition, 1, 2, 3, 4, 5, I've got 10, and then 1, 2, plus 7 is 9. So we have 19 successes out of 50. When you divide 19 by 50, you get 0.38, and that as a percent is 38%. So there's a 38% chance. The experimental probability says that there's a 30% chance that there will be a reaction in both beakers. I'll go ahead and do it. So the goals homework is the following. Use a tree diagram to find the sample space and the total number of possible outcomes. So we have Spider-Man, Iron Man, Thor, Captain America. And they're being paired off against Green Goblin or Kingpin. Again, the Green Goblin or Kingpin. Again, the Green Goblin or Kingpin. And the Green Goblin or Kingpin. So we can see that there's 8 outcomes. And we want to know what's the probability that Spider-Man will battle the Green Goblin. So there's 1 of those amongst the 8. Yeah, this one. I need to watch out for the spacing on these things next time because I miscounted this earlier today with a student too. So, yeah. There's 1, 2, 3, 4. 4 types of armor. There's 1, 2, 3, 4, 5, 6 types of weapons. And then there's 1, 2, 3, 4, 5, 6, 7 types of spells. So we're going 4 times 6 times 7. 6 times 7 is 42. 42 times 4 is 8. Carry the nothing, so 168. So there's 168 loadouts. Yeah. All right. Doing this one. You randomly guess 5 true-false questions. Well, true-false has the probability of 50%. So that means we're going to use the numbers 1 through 5, meaning 0 and then 6 through 9 are failures. So we want to design and use a simulation to find the experimental probability that you answer exactly 3 questions. You correctly answer exactly 3 questions. So we only want 3 of these to be correct. So here we go, plugging through. We only have 1 correct here. We have 1 correct there. We have 1 correct there. 2 correct in this one, 2 correct in this one. This one has 2 correct. This one has none correct. This one has exactly 3 correct. This one has exactly 3 correct. That one only has 2 correct. This one has 4 correct. This one has exactly 3 correct. This one has 4 correct. This one has none. This one has 3 correct. This one has 4 correct. This one has 4 correct. This one has exactly 3 correct. This one has 4 correct. This one has 4 correct. This one has exactly 3. This one has 4. This one has 2. This one has 3. This one has 2. This one has 2. This one has 3. 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 This one has 4. This one has 2. This one has 4. This one has 3. This one has 2. This one has 2. This one has 4. This one has 4. This one has 4. This one has 3. This one has 4. This one has 3. This one has 1. This one has 3. This one has 2. This one has 3. This one has 4. This one has 4. And this one has 2. Or 3, sorry. So now if we count them up, we have 1, 2, 1, 2, 4, 2, 3, 2. So if we add these, 1, 2, 3, 4. Wait, why did I say 1? That's 2. 1, 2, 3, 4, 5. So we've got 10. And then 1 plus 4 plus 3 is 8. So we have 18 out of 50. 18 out of 50 is 0.36, and 0.36 is a percent, is 36%. So our experimental probability of getting exactly 3 questions correct is 36%. At a shopping mall, 40% of the shoppers are willing to take a survey, so that's 1 through 4. Estimate the probability that out of the next 5 random shoppers, there will be 3 or more in a row that are willing to take the survey, so that's 0, and then it's 5 through 9. We want exactly 3 in a row to make a survey. So one thing that I did when I first did this problem is if the middle number is not a 1 through 4, I can eliminate it. So if the middle number is not a 1 through 4, I can get rid of it. And that to me is an important piece of information because I feel like with that information, I can really go through this a whole lot faster. And the reason why I can get rid of the middle one is because no matter what, if the middle one is, so like for instance, with this being a 6, that means I can't have 3 in the row because I can't have a 1 through 4 on the left and the right and be 3 in a row. So this one here is gone. This one here is gone. This one here is something to look at, but it's got a 1 and a 3, so that's not good. This one here is something to look at, but it's got a 4 and a 5, so that's not going to work. This one here, it's not going to work either. Well, this one here, the 2's in the middle, but it's got a 1 and a 0 on, so it doesn't work. The 4, 1, 1, this one does work. 1 in the middle, nope, because 7 and 9 and 0, 0, none of those work. 7 in the middle, I can skip. 7 in the middle, I can skip. 3 in the middle, but not enough. 1 in the middle, and that's going to work. 5 in the middle, but the 3 is separated by a 6. 7 in the middle, so skip it. This one does work. This one won't work. This one won't work because 5's in the middle. This one won't work because 5's in the middle. This one does work because 3, 3, 2 is 3 successes. 4, 5, nope, that's not going to work. 6 in the middle, not going to work. 1, nope, not going to work. 7 in the middle, nope. 8 in the middle, nope. 9 in the middle, nope. 0 in the middle, nope. 2, 1, 2, 4. Well, 4, 2, 1, that's going to work. Here, 2, 3, 6 doesn't work, nor does 5, 3, 2. 0 in the middle, skip it. 3 in the middle, but 6 is on both sides, so skip that one. 2, but 8 and 5 are on both sides. 7, not going to work. 4, surrounded by a 1 and a 3, that's going to work. 5, that's not going to work. 8, that's not going to work. 0, not going to work. 4, but it only has a 2, so doesn't meet the requirement. 5 in the middle, not going to work. 6, not going to work. 4, but it's surrounded by an 8 and a 0, so that doesn't work. 0, surrounded by 7 and 1. Well, 0 doesn't work anyway. 5 doesn't work. 7 doesn't work. 9 doesn't work. 8 doesn't work. 6 doesn't work. 1 is not surrounded by the right numbers. 9 doesn't work. 4, 1, nope, that doesn't work. 9, no, nope. So, looking through here, we've got 1, 2, 1, 1, 1. So that would be a total of 6. 6 out of 50 And so 6 out of 50 is 0.12, and 0.12 is 12%. So we can expect that 12% of the shoppers would be willing to take a survey, of 3 or more in a row would be willing to take a survey. So that's this. Thanks. Bye.